So in this video, I will be going through the procedures for reducing the total scanning data measured on time-of-flight instruments at SNS facilities, such as Nomad and probably Powder as well. So the software we're going to use is called ADDIE, and the software has already been deployed on the analysis cluster. And to connect to the analysis cluster, either we can go to the website analysis.sns.gov to connect to the cluster using the browser by hitting this launch session button, or we can use the recommended Link software. That's what we are using today for the demo purpose, as shown on the right hand side, to connect to the analysis cluster. So either way, it should be working. And once we connect to the analysis cluster, what we can do is go to the application terminal to launch a terminal, and then from there we type in the command ADDIE to start the program. And for today's demo purpose, I will be following this documentation on the left hand side website. So to get access to the documentation, we go to the powder.ornl.gov and go down to the total scanning section and the data reduction, and further go down to the data reduction how-to. So that's how we can get access to the data reduction documentation. So for today's demo purpose, I will be using the dev version in my local area, but basically the interface is exactly the same, and it's just the version is in my local area, so it contains some advanced features that we are trying to get deployed to the production version as soon as possible. So here what I will do is to execute this command to launch my local version. Okay, so just after a short while, the program will be launching and you will see the interface. So before I start, just a little background about the ADDIE software. So actually, ADDIE software is just a front-end interface for the underlying engine for reducing the data. And historically, we have been using the autonom approach for reducing the data. So that's the interface we are seeing here on the right-hand side. And beyond that, actually, we have been developing, and now it should be ready for users to use another engine for reducing the data called mandated total scanning. So that's what we are trying to use today for the demo purpose. So ADDIE as a front end has the parallel interfaces for these two types of underlying engines. And we strongly recommend the future users to use the mandated total scanning engine as what we are going to demonstrate today. So the default interface is still the autonom, and to switch to the mandated total scanning interface, we go to the File, Settings, and click on the mandated radio button to switch to the mandated total scanning interface. So once we have the interface launching up, what we can do is, actually what we are seeing is a blank space in the middle. That's the place where we are going to populate the table with some information about our samples and also our IPTS, the experiment, for us to use for reducing the data. And as detailed in the step 2 here on the documentation page, we have multiple ways to populate the table. So I will go through each of them just one by one briefly to give you a flavor about how things are really working. So the first approach is change to the IPTS. So again, the little background knowledge is that we have deployed an auto reduction workflow for reducing data as the data is being collected during the experiment. And once the auto reduction stage is finished, when the data is being collected, it will just create some intermediate files and also some configuration files for us to load in later on. So that's exactly what we are doing here. By changing to the IPTS, which is the unique ID for the experiment, what ADDIE will be doing is to search the auto reduction folder for alternative or usable configuration file to be loaded into the table automatically. So that's the basic idea. So here I will just use a calibration IPTS, which contains a lot of calibration and characterization runs, like diamond, vanadium, empty instrument, and so on and so forth. So this is the IPTS we're using here, and by clicking on OK, it will just, as I said, to go to the IPTS, search for any usable configuration file that can be loaded in. So here I just, for the demo purpose, I run a manual auto-reduction procedure to create a single row in this IPTS. So that's what we are seeing here as loaded in. So that's the first way to populate the table. And let's clear the table for the moment and go to the second way. The second way should be changing to the working directory. So if you right click to bring up the context menu, you will be seeing the option shown on the top, change to working directory. So basic idea is the same as changing to the IPTS. And the only difference is that in this case, we have the capability to select the working directory manually by bringing up a file browser. So by using this browser, we can go into the directory we want to use and select the directory. So I will be using this directory. And the thing happening behind the scene is exactly the same. So what the ADDIE will be doing is to go to the directory selected, the working directory, and search for any usable configuration file to populate into the table. So that's the second way. The only difference as compared to the previous way is that for using the IPTS way, it's pretty much very dedicated and very specific IPTS folder to search from. So that's about the second way. And before I move on to the third way, what we can do is once the table is populated with contents, and once we correct all those information, what we can do is go to the table, export, to select a location to save the configuration into. So I will just use this file, overwrite it. So as you can see, the table now is exported to an external file. And by having that external file, what we can do later on is we can, say for the moment, we clear the table again. We go to the table again, and we can import a previously saved configuration file by go to the table, this option, and hit replace. And then browse into the file we just saved, and hit open to load it in. So you can see now we have loaded in successfully the previously saved or exported table. So that's the third way. And let's clear the table again to move into the final way of populating the table. So suppose that we haven't run auto reduction, we haven't got any previously saved configuration file for us to load in. We have nothing to start from. So what we can do is to start from scratch. For sure, we can use the menu options to say we want to insert blank row and to fill in the information manually. But what we can do instead is to go to the fourth way, go to the table, import from database, and hit replace. So what the program will be doing is that it will interact with the OnCat database, which is the ORL database for hosting the sample information and the experiment information stored in the database. So what we can do here is to interact or bring the information available from the database to the table by logging in with our UCAM's credentials. So if I hit the replace button, and then what we can do is to log in with our UCAM's username and password. So we get access to a whole bunch of IPTS, which we get access to. Because I'm a team member, so instrument team member, so I have access to a lot of IPTSs. But in general user case, probably you have very limited selections. So you can use the selection menu to conveniently select IPTS. Or what you can do is to go to the right-hand side box to put in the IPTS manually. Like in this case, I will using the demo again IPTS. Hit enter, so you can see now the table is populated with contents. And what we can do is to hit the import all runs to move or to bring all the runs information to the table. And another way is we select the run button radio button on the bottom, and then put in the run numbers to just import a specified run number information instead of bring in all the run numbers in the IPTS. So I will go back to the IPTS way, select the IPTS, and then hit import all runs. So that's what we are seeing here. So that where we have a whole bunch of options to merge the repeated runs. So the idea is that during the experiment, we will have, in most cases, have multiple repeated runs for the same set of sample measurements, just to accumulate statistics. And later on, for sure, for the same set of measurement, we have multiple run numbers. So for sure, we need to merge them. And we have multiple criterion we can use to merge the different runs. So the first way on the top is using the raw title. So each run number, it will be having a unique sample title. Not unique, but have a sample title. And they should be unique, actually. And we can use that for merging the runs. The second way is roughly the same as the top one, but it will just remove the dynamic temperature information. So during the experiment, the data collection engine will be appending a dynamic temperature, which kind of instantaneous temperature corresponding to the measurement to the sample title. So sometimes, or in most cases, it will be not useful for pinning down the run numbers and measurement. So we probably want to remove the dynamic temperature from the sample title by default. So that's the default option the second way. So by selecting it, we go to the hit on the OK button to import all the runs available in the IPTS. So that's basically the first way. So now you can see the table is populated with contents. And then what we need to do is to manually populate all the missing informations in the table as needed. So I will go back to the first way just for demo purpose to select a demo run to move on. By putting the IPTS, we bring back the little table for the demo purpose, and then we move next. So that's the step 3 here. So step 3 is mainly about the calibration. And that file is mainly for transforming the time of flight space data to the D space by having a pixel by pixel DFC values for the transformation. So that's the file that should be prepared by the instrument team once we finish the run, for example, for a calibrant. The standard sample and yearly nomad and pattern is type diamond to be used for the calibration purpose. And because in this case, we have been going through the auto-reduction procedure, which will be preparing the calibration file automatically and saved into the configuration file. By loading in the IPTS, I can see at the bottom section, the calibration file has already been ready here. But in the general case, we probably need to, or sometimes we probably need to browse into a H5 file, which save the pixel by pixel DFC values as the calibration file, and then we can select it to load it in by hitting the open button. But here I will skip this procedure to use this default calibration file coming with the IPTS. Oh, as the instrument team, we also can hit on the make button to prepare a calibration file by using this interface. But because in most cases general user will not be using it, so I will just escape the make calibration step. So that's about the calibration. The fourth step is some advanced configuration for the data reduction. So to do that, we can go to the reduction configuration button on the bottom left corner. Click on it, it will just show up the advanced configuration parameters for controlling the behavior of the data reduction. So in most of the cases again, general users will not need to configure them, but just in case we need to, we can put in the parameters here in this mainly the PDF and also the global aligned focus arguments section. So that's probably the only two places that general users in rare cases will be configuring. So the PDF section is straightforward to understand. What we can input here is the Q range for performing the Fourier transform, and also the R range together with the delta R, the interval, for the real space data that is created from the Fourier transform. So that's about PDF, and the next section is about align the focus. So that's basically concerned about, as the name suggested, align focus, align different pixels, and focus all the pixels in a certain group into a single pattern. And there are a whole bunch of parameters behind the scene controlling the behavior of the aligned focus. And because we are using the mentate aligned focus powder algorithm behind the scene to do the job, so what the general users can do, you can follow the link on the left hand side documentation page. By clicking on this link, you will be brought into the aligned focus powder documentation page of the mentate algorithm. So you can see here we have detailed documentation about what those specific parameters are really meaning. So that's what we can do. And here usually there are two parameters that we probably sometimes need to change a little bit. The first one is the t-min. Basically, it's the minimum time of flight value we want the data to present the ways. So say nomad, usually we use the 300. That's in the microsecond unit. And the next one is for sure the Tmax, which is the maximum of the time of flight space pattern. And usually something like 20,000 should be okay. So that's about it, and that's, as I mentioned, probably the only two places that we want to change the parameters. And changing the parameter, we can hit the save and the close button to go back to the main window. So the final configuration is about the output directory. For sure, we want to tell the program where to save the reduced data. And to do that, to see or change the option of the output directory, we can go to the File menu, click on Settings to bring up this little setting window. And down below, we will find the output directory. So currently it is using this directory. And that's because we have been going through the auto reduction procedures. All the things were just configured automatically. But again, if you want to change the output directory, you can click on this browse button to bring up the browser and select the directory that we want to use for hosting the reduced data. So here I'll just click on cancel and just use this default option coming with the IPTS. So that's about number 5 step in the documentation page. So once that step is done, we should be ready to go ahead to click on the run button to kick off the reduction. Sorry, I was suffering from the allergy situations, which is very typical Tennessee thing. So I have to pause the video record and then come back again to redo it. But basically, once the number 5 step is ready, we can move ahead to reduce the data to kick off the reduction. So what we can do here is to select the drop-down menu to select the PDF from the list and then click the run button on the right hand side to start the reduction. And once we launch the reduction job, you'll see a little window popping up. And that's the job management, giving us some information about the job running behind the scene, including job name, the launch time, and also an abort button shown on the right hand side. That's the place where we can hit to stop the run or to abort the running. Sometimes we'll be finding that maybe something wrong is happening or some configuration is not right. So we can click on the button to stop the run and reconfigure it. And after, well, as you can see now, the job is done. And once it's done, the status will be changed to the done, as you can see here in the window. And that's indicating the job is finished. So we can now click on this little button to click the job manage window and go back to the main interface. And then we move on to the step 7 here, which is to, for sure, to check the output. And because here we are using this output directory, as shown here. What we should do is to go to this directory from the terminal or from the file browser, whichever way you like, to check the output. So that's now go back to the terminal, and that's exactly the directory I'm located in the terminal now. So that's our output directory, and then we do an ls to list out all the files in the directory. So that was created during the reduction. And so we have the Jesus data reduced, we have the log files, we have the SFQ. Those two directories were generated from the following steps, because I have already run the following steps for the demo purpose previously. So those two directories were already created, but normally after a normal reduction run, we only see these 4 directories, these 3 plus the topaz at the bottom. So each directory contains the reduced data in different formats: Jesus, SFQ, and also topaz, together with the log file. So that's about the output. So from the output, you can see we have the SFQ data. So the SFQ data following the currently used mechanism is reduced to a bank-by-bank format. And the reason why we're doing that is we try to use the high-angle bank, which is a high-resolution bank, bank 5 here, specifically on Nomad, as much as possible, because that one, as I said, is highest resolution because the scanning angle is large. And we want to use that bank as much as possible, so that's why we reduce the data to a bank-by-bank form. And by doing that, the little disadvantage is that we need to load in the data, reduce the bank-by-bank SFQ data, and merge them manually, because it's very difficult to determine automatically the range we want to use for merging all the banks together in a seamless way. So that's why we have this number 8 step here, which is the post-processing. So if you go to the post-processing tab on the top, and that's the interface we're going to use for doing the post-processing to merge the data and probably perform the following forest transform step. So let's start with the first step, as indicated by number 8 here, to load in the reduced bank-by-bank SFQ data, to extract it, put in the parameter for merging it, and then finally just merge it. So that's the thing we are trying to do here. So first thing, click on the load button and find the directory, which is the output directory, and go into the SFQ and select this file, which was reduced to a bank-by-bank form. Clicking on it, load it in, and click on extract to extract the bank-by-bank data, because the data will be reduced that we saved in the Nexus format, which is kind of a compressed format. So we can use this button to extract the available workspaces. Usually we just have one workspace which contains normalized SFQ data in, again, a bank-by-bank format. So once we hit that button, we will see that the file list will be updated to show all the available files in this reduced data. So from bank 1 to bank 6. And the next thing obviously is to fill in the parameters for each of the bank by making the selection bank 1, bank 2, bank 3, and so on and so forth, to put in the information or the parameters corresponding to each bank, including the Qmin, Qmax, and offside and skill for the Y data for each bank, and then finally merge them. So the principle here is that for the bank-by-bank parameter, the Qmin, Qmax, we want a seamless connection from bank to bank. Say for example, the bank 1, I will be using 0.5 to 1, and the bank 2 will be starting with 1, say from 1 to 2, and the number 3 is, for example, 2 to 4, maybe something like that. So we want to guarantee a seamless connection and non-overlap connection between the banks. So that's the principle. And offside Y skill is sometimes it will be useful to offside the Y data and scale the Y data a little bit to guarantee again a seamless connection between the banks. And here the plot window on the left hand side will be useful, because to make sure that the bank will be seamlessly connected, we have to visualize it. So for example, I select the banks 4 and 5 here, and then right click to bring up the context menu and click on the plot. And then that's where the place on the left hand side we can go into like the region we are interested in and guarantee and make sure the bank is connected in a seamless way. For example, in this case, probably we can select this region or probably this point as the connection point between the number 4 and number 5 bank. So that's the basic idea of the plotting and visualization for the merging purpose. So here again, for the demo purpose, I will be using the configuration file that we previously saved and loaded in to load in all the parameters corresponding to each of the banks. So to do that, we can go to the load config button here and then browse into the previously saved configuration file. So here I will be, I think, let's go to this file directory and go to shared test data. So that's the previously saved configuration file that I created for this demo purpose, this guy. Hit open, and once we do that, you can see that now all the parameters for all the banks are ready. So bank 1 is from 0.5 to 1.75, and the number 2 bank is not used. And to specify that, we just put all zeros for Qmin and Qmax. And number 3 is starting from 1.75. As remember, we should guarantee a seamless connection between the banks. So number 3 bank will be starting from 1.75 until 3.12 and so on and so forth. And accordingly, we have the Y offside and Y skew parameters well populated automatically. And once we have the configuration populated in properly, we can then hit the merge button to merge all the banks. So you can see that once we do that, the right hand side file list menu or the panel will be updated. So let's clear the canvas again and right click on the merged data to plot it. So you can see now we have the merged SFQ data. And you can use again the visualization window to inspect whether the data is merged properly. So that's about merging. And for sure, once the data is merged, we make sure everything is working properly. What we can do is corresponding to the load config button, we can have the save config button to save the configurations to an external file, like what I did before for this demo purpose. So we click on the save config file, save config, and then select the location. Say this is silicon demo merge.json file. So it's in a JSON format. So once we have done that, you can see it says the file successfully saved. So that's about saving. And then once the data is merged, we have the merged data on the right hand side. And what we can do next is to go to step 9 here, which is about the Fourier transform. So here for doing the Fourier transform, we will be using the program called PyStalk behind the scene. And ADDIE just provides a front-end interface again for doing the PyStalk processing. So that's a little section in this middle panel here, as you can see, and that's highlighted with the right rectangle on the left-hand side documentation page. So here in this panel, we can just populate a whole bunch of parameters concerning the PyStalk processing to do the Fourier transform and probably to do the Fourier filter as well, something like that. And here I won't go into details about those parameter settings. So to get further idea about what's really happening behind the scene and to know about which parameters are meaning what, you can go to this left-hand side section from the menu, go to the post-processing under the total scaling data reduction section. So here, if I click on it, it can just bring up a documentation specifically concerned about this middle panel or this bottom panel configuration for the PyStalk processing. So as I said, I don't want to go into details about them. So what I will do is again to load in a previously saved configuration, as you can see here. using the button load config. So then I will just browse into the directory that we just used a moment ago to load in the PyStock JSON configuration file. Click on open, and it will just populate all the necessary parameters. And then once we have the parameters ready, we can save the configuration again to an external file. And once we have done that, probably the only thing we need to do next is to click on the stock button shown at the bottom to kick off the stock running the processing. And as you can see behind the scene, there is really something happening, and after a short moment the file will be ready. So you can see the little information popping up at the bottom, and then this file section about the stock data will be ready. There are some intermediate files created for doing the Fourier transform, like the first two is the skilled S of Q and also the G of R data for transformed obtained from the Fourier transform. And FT ones are the same set of files but with the Fourier filter applied to remove the lower range garbage. And then underscore RMC is that after the Fourier transform, after the Fourier filter, we then transform the data into the reverse Monte Carlo ready the data. So that's by saying that, basically that's the data ready for RMC profile analysis. So that's what we have here. And underscore RR here is sometimes it could be useful because even by applying the Fourier filter, still will sometimes have the lower range garbage be below the first peak or below wherever the first peak signal what we believe belonging to our sample. So below that is not expected any signal. So what we can do is to like brute forcefully force the low R range region to be on the baseline. So that's what we can do by giving these three parameters shown in this input box and then obtain the underscore RR GFR file. So that's about the stock. So here for both the merge and the stock section, both of them are mainly for the individual processings, and that sometimes can become tedious. Although we can do that one by one for all our measurements, but that's not probably practical in practice, because in practice we may have tons of measurements or samples, and to go through them one by one is very, very tedious or even just impossible manually. So what we can do is that we can select some typical runs and going through this post-processing tab to get a feel about the parameters, either for merging or for the stock PyStock processing. And then, as we have already mentioned, we can save the configuration to external files, again for both the merge section and also the PyStock section. And then what we can do is we go back to the processing tab. And then here you can see in the drop-down list, along with the PDF selection or the option, we also have the merge and also the PyStock selection. So say we want to merge files or all the rows in the table here in a batch manner, so process them all at the same time. We can go to select the merge option and then click on run. And then what we can do is to browse again into the previously saved merge configuration file. So that's the exactly same file as we were using for doing the post-processing in another type. And here I select it again to use it. And once we select it behind the scene, you can see now something is happening behind the scene to merge the data, because in this case we only have one row, so there's really not so much thing to do. But in practice, if you have multiple rows, by clicking on the check box, we can then select a whole bunch of runs and kick off the merging options in the series of batch manner. So that's the thing about merge. And similarly, we can do the same thing for the PyStock as well. Also, by selecting the PyStock option, we can go to the run and select the file we want to use, like this guy. And you can see now really something is happening behind the scene. And once the job is finished, you can see the little warning message or reminder message down below. So that's about the batch processing of both merging and also PyStocking. And I think that should be it. And let's scroll down to the bottom section. That's about number 10. So number 10 is just the batch processing for merge and also pass dogging. So that's about it. So after I finished, I realized I forgot one thing, which is how to check the merge and the PyStalk data. So again, we go to the output directory, like in this case. That's the exact same directory we were inspecting, checking those reduced data files, Jesus, logs, SFQ, Topaz. And here are the two extras folders that we were mentioning, which should not be created at the reduction stage, but they will be created at the merging and PyStalking stage. So this folder is contained, the SFQ underscore merged is containing the merged data. You can see this bank by bank extracted data and also the merged SFQ data together with the merged configuration file saved automatically once we click on the merge button. So that's about the merging. And then this stock directory is containing the stock data. So you can see all the files, GFR, SFQ, and FT for the filter, and also the RMC files that we were seeing before. So that's really about it, checking the output. Thank you.